Okay, so what we're going to talk about now, we're going to start off by talking a little bit about why earthquakes happen at all. So what we kind of know about earthquakes and the causes of them. And then we're also going to talk a little bit about what happens in an earthquake. So we're going to talk a little bit about the different waves that an earthquake produces. And we're going to see a video of the effects of those waves. Nothing too graphic, I promise. And then once we've done that, we're going to talk a little bit about the earthquakes which we felt over the weekend. I say we felt, I have to admit that I didn't actually feel them myself, which I'm a bit disappointed about. And so we'll talk about the one which happened quite a long way away at the plate boundary to the south. And we'll talk about the two smaller earthquakes, which are what people felt in and around Cape Town. And then once we've done all that, we're just going to have a couple of slides which is going to tell you what you should actually do if you are ever unlucky enough to actually be in a strong earthquake, because there's a few simple things which can make you a lot safer. So I'm a lecturer at the Department of Geological Sciences, and another thing I want you to maybe take away from this talk is that geology isn't all about mining. So we study the earth in all of its many forms and its many activities. So I should probably just maybe briefly explain the slide here that I've got as my title slide. And I've got this here because it really explains one of the reasons why I actually study earthquakes and why I spend my time researching them as one of my main research interests. What you're seeing here is actually a satellite imagery of a place in Iran. And during my PhD, I spent a lot of time studying Iran. And this structure that you see from a satellite imagery is a citadel. It's like a historical building, which was in a place called Bam. And this area was actually destroyed in 2004 in an earthquake. And some of the people who I kind of knew through the university who were in the research group were actually Iranians. And so they were involved in the kind of aftermath of this. And it was a very devastating earthquake. And seeing how they responded to it and how it affected the people that lived there was one of the kind of my motivations for getting involved in this kind of study. And you can see on the left-hand side what it looked like beforehand, and you can see the structure with all of its domes. And then on the right-hand side, you can see what it looked like after the earthquake. And you can see that these like historical buildings were completely destroyed, basically. Okay, so if I can just move on. Okay, so to understand why earthquakes happen, you have to understand a little bit about the Earth, because it's not obvious that we should get earthquakes. So if you look at a lot of the planets in the solar system, you don't actually expect there to be earthquakes on them, or at least not the large ones that we get here. And the reason that we get earthquakes on Earth is because the Earth is like basically acting as a heat engine. And what I mean by that is at the center of the Earth, the core of the Earth, is actually a solid metal core. So what this piece of rock is actually a bit of a core of another planet. And this actually came to Earth as a meteorite because the other planet was hit by a big meteorite and bits of it broke up and some of them ended up on Earth. And this is one of them which actually came from the core, the center of that extraterrestrial planet. And you can see that it's made mainly of iron. So you can see that this is metal. And this metal iron core is gradually growing. So you've got this solid core in the middle, and then around it, you've got a liquid iron core. And that solid core is gradually freezing, it's gradually expanding. And as it does that, it's basically passing heat onto the material around it. And the material around it is this green stuff. So this is what the mantle looks like. This is like what most of the Earth looks like. So all the way from basically the surface down to 6,400 kilometers, we've got this, 2,900 kilometers, we've got this green mantle rock. And this rock can actually flow, okay? So what's happening is this rock is getting heated up at the bottom. And as it gets heated up, it becomes less dense, so it becomes buoyant. And then it's rising up towards the surface. And then over here, it's getting cooler and it's sinking back down again. And that rising and sinking hot material basically exerts a force on the base of the top part of our planet. And that top surface part of our planet is divided into a whole set of fairly rigid areas, which we call plates. So basically what this map is showing you is all of the different plates that we can see on the Earth. So you've got the kind of Eurasian plate over here, you've got some big plates in the oceans like the Pacific plate, and you have the African plate over here. And so we're down here towards this, like the bottom part of the continental part of the African plate. But what you can see is in between these plates, you have a whole series of black lines, which are the plate boundaries. And so if we take maybe this Pacific plate here, the Pacific plate is moving in this direction. And then you have the plate over here, which is moving in this direction. So you can see that they're moving towards each other, okay? So you have to have relative movement between the two sides of the plate boundary. And that movement is taken up by earthquakes. So basically the earthquakes are kind of an expression of this movement between these relatively strong plates. So if you look at where you actually see earthquakes in the world, you end up with a map like this. Okay, so these are only the big earthquakes. These are basically the earthquakes which are about the same size as the one that first happened on Saturday, a long way away from Cape Town to the south. And on this diagram, you can see lots of these little white dots. These are these big earthquakes which are happening on plate boundaries. So you can see that they're kind of forming lines around the edges of the plates. And almost all of these big earthquakes, which are damaging, which are dangerous, happen on these plate boundaries. Sometimes the plate boundaries are quite narrow. Sometimes they're kind of a zone which is a bit wider. So you get that kind of in the area north of India, in Eurasia up here. But as well as all of those earthquakes which are happening on plate boundaries, there's also a few earthquakes which are still big, which happen in the interiors of the plates. And so on this diagram, those are being shown by the red dots. So you can see that there's not that many. This is basically all of the earthquakes which have happened over a period of around 50 or 60 years. So this is like quite a long time scale of big earthquakes. One thing that you probably notice is that there's a red dot, which is basically pretty close to where we live, right? Like there's a red dot in South Africa in the Western Cape. And I mean, that is a sign that even though we're not on a plate boundary and earthquakes are uncommon, they do sometimes happen. And that red dot is there because in 1969, so about 50 years ago, there was an earthquake just to the east of where we are now, if you're in Cape Town. And that was the magnitude 6.3 series Torbach earthquake. And this isn't a huge earthquake, but it is something which is big enough that it can cause damage. And you can see in the background of this photograph, you can see that some of these houses have been damaged. And there were actually a few people that were killed in this earthquake. So it was about 12 people actually died in the Western Cape from this earthquake. So even though we're a long way from the plate boundaries, earthquakes are quite unlikely. They do occasionally happen, okay? And they can even be these relatively large ones. So the reason that I've put this slide in is it basically is showing you all of the earthquakes in the world which are big enough to be recorded, which happened in the last week. So this is 7 days of earthquakes. And you can see this big circle here, actually pretty big, like one of the biggest earthquakes, possibly the biggest earthquake in the world that happened in the last week was on the plate boundary. So this red line is the plate boundary to the south of Cape Town, to the south of South Africa. And we'll talk a bit more about that later. And you can see you've got this smaller dot here. These are the ones which you may have actually felt. These are the ones which happened much closer to us. But I also just want you to kind of notice that if we look over the whole world, on a lot of these other plate boundaries, actually there were quite a lot of earthquakes. So these aren't actually that uncommon things. Like it might be unusual here, so we don't often feel these earthquakes which are strong enough for us to kind of actually detect them ourselves. But if you look on kind of a global scale, this is something which is happening all the time, every day. There are significant earthquakes that you would be able to feel. In some places, you can see a lot more than others. So for instance, the coast of South America here would be somewhere where they get quite large earthquakes very regularly. So why do we have earthquakes? What is an earthquake? So we've said that these plates are moving relative to each other. So, you know, we might have a plate boundary zone, and in this case, we're looking at a kind of a cartoon of a particular plate boundary zone, which is where the Indian plate, the Indian Ocean, is being pushed underneath Sumatra. So Sumatra, and this is basically, if you go across the Indian Ocean from South Africa, you're going to get to this area. And so what happens, the reason that we have earthquakes is this plate is moving downwards underneath Sumatra, and it's moving at maybe a centimeter. Well, no, so this is actually quite fast. So this is moving at 7 or 8 centimeters per year. So every year, this is moving down by 7 or 8 centimeters. But in between earthquakes, the interface, the boundary between the two plates, the Indian Ocean and the Sumatra plate, is locked. They're tightly held together, and the two sides can't slip relative to each other. If you were looking somewhere in the interiors of the plates, so something more like around here, or even in maybe more rapidly deforming areas in here, but still in the interior, rather than it moving at centimeters per year, you would still have a fault, but it would be moving at maybe less than a millimeter per year, so very, very slowly. So as this plate moves, the rock's cold, it's hard, so this interface is locked, it can't move. So what's going to happen is the plate that's going down is going to drag down, it's going to bend the plate above it. Okay, so basically it's like bending a ruler. You're storing elastic energy as the one plate gets bent by the other plate moving down. And that energy, that elastic energy, is going to build up and up and up. And eventually it's going to get so large that this fault, this locked region, which is shown in red here, is no longer going to be able to support all of those elastic stresses. And what happens then is the fault is going to break, it's going to snap. And as soon as it does, then all of this elastic energy, which has been stored up over this really long period of time, is going to be released. And this upper plate is going to snap upwards, okay? And it's that release of that elastic energy, which has been stored over a really, really long period of time, that's the earthquake. That release of energy is what causes the waves, that causes the shaking. So this is actually, I know that some people have already asked questions about tsunamis. When you get a tsunami, this is also what causes a tsunami, right? So basically what's happened here is this upper plate, when it breaks, it's moving upwards, okay? And if your plate is underneath the ocean, then as it moves upwards, it's going to push the whole water column upwards above it. So you're going to get like a step in the surface of the ocean. And that's what causes a tsunami. So the water is then going to flow down to level out that step. Okay, so it's the vertical motion of the fault when that elastic strain is released, which is actually causing the earthquake. So what does this look like? So this is an actual photo of the area that cartoon was of, okay? So if you remember in the picture before, we saw that there was like a little island. This is that little island, okay? And what you can see here is you can see a bunch of palm trees. And the interesting thing here is that this photo was taken before the earthquake. And what you can see is you have these rows of dead palm trees in the center of the image, okay? So why are they there? They're there because the farmer went and he planted his palm trees in rows. when that ground was above sea level. But as the plate, the downgoing plate, moved downwards, it was pulling down that upper plate as the elastic energy was being stored. And it's pulled it down so much that now these trees have gone below sea level. And because when you go below sea level, you get the salty water, the salty water kills the trees. And so that's why you have all of these dead trees here. Okay, so this is what you're seeing here as evidence for that plate being pulled down. Okay, so now I'm going to show you the same place, but after the earthquake. So that's what that looks like. So you can still see these dead trees, but you can see they're no longer underwater now. They're no longer below sea level. This whole island's got much bigger because it's popped out because of the earthquake, okay? And so you can, here you're seeing that elastic energy release. So that's basically what an earthquake is. It's this gradual building up of this elastic strain. It's this bending of the plate, and then it becomes too much for the fault and it breaks, and you release all that elastic energy at once, and then that's what causes the earthquake. Okay, so you can actually see like a record of this, like in this same place, the same island, you can see a whole record of this happening again and again and again. It's like a cyclical process. So all of these funny kind of stick things at the bottom, those are corals. So they grow underwater. And then this black layer on top is peat, and that forms when it's above the water, when it's at ground level. And then on top of that peat, you have more corals growing, more of these funny little tubes. And now this is above the water again, because it's after the earthquake. And so you'll get a new layer of peat forming. So as that plate moves down steadily for thousands, millions of years, it's going to build up the strain and release it, build up the strain and release it. And that cycle is the earthquake cycle. Okay, so what happens in an earthquake? This picture basically shows you kind of a worst case of what an area might look like after an earthquake. This is not in any way normal. It was a very big earthquake, and there were very specific things about this area that caused this very severe damage. You can see all the trees have fallen over, the houses are tilting. What happened here is this is an area where the surface is rigid, it's frozen, it's permafrost, and then underneath you have more liquid material which can kind of move during the earthquake, and you get this dramatic picture. But another way of like thinking about earthquakes, or a way of describing earthquakes, is this idea of the magnitude. So you've probably heard of like earthquakes being described as magnitude whatever. So the earthquake which was far away to the south was about a magnitude 6.1. The earthquake which was closer to us, which we felt, was something like a magnitude 2.7, around that kind of size. So what does that mean? What does a magnitude mean? So like basically what the magnitude is it's basically telling you how much energy has been released. And so the more energy that's being released, the stronger the shaking, the more damaging the earthquake is. So like how much energy was actually released in these earthquakes? Well, the first one that happened, the one which was to the south, that was actually quite a lot of energy. So it was a magnitude 6.1, which is about the same energy as was released by the Hiroshima atomic bomb that was blown up in Japan. And that would have been tens of thousands of tons of explosive. That's like how much kind of conventional TNT explosives you would need to release the same amount of energy as that one earthquake, which was the first one that happened. In terms of the ones which actually happened much closer to us, that's down here. So it's described as the minor earthquake. That would be kind of the terminology. And you're talking about maybe a couple of 100 kilograms of explosive, a couple of 100 kilograms of TNT, which sounds like a lot. I know that you don't want to be anywhere near a couple of 100 kilograms of explosives when it blows up, but you have to remember that this earthquake was like deep down beneath the surface. So like if you're 5 kilometers away from that explosive and there's rock in between you and it, then it's not so scary, right? And so that's why maybe you feel some rumbling, but it's not something which is going to kind of cause your kind of house to collapse or anything like that. So one of the, and actually also kind of to put it into perspective, the amount of energy that was released in these earthquakes was about the same as a lightning bolt, actually. Like it's a different type of energy. So it's not the same kind of light and heat energy as in a lightning bolt, but in terms of just the amount of energy, the number of joules, it's about the same amount. And these little earthquakes, you actually get a lot of them. So there's like, there's a law, a kind of a rule of thumb, which says for every order of magnitude you go up, you get about 10 times fewer earthquakes. So if you look around the world, you get hundreds of thousands of these small magnitude 2.7 or so earthquakes every year. Okay, so they're really common. They're happening all the time. Okay, so there's another way that we can measure earthquakes. And the other way that we can measure them, the other way we describe them, is what's called the Macali intensity scale. And so this is how we estimate the size of earthquakes based on what people tell us they felt in the earthquake or what they saw in the earthquake. So the earthquakes that we had in Cape Town would have had an intensity of about 3 or 4. Okay, so the description of that is felt quite noticeably by persons indoors, especially on the upper floors of buildings. If you're higher up in a building, you'll actually feel it more as the building rocks. Many people don't recognize it as an earthquake. I think that was the case for this one. A lot of people weren't really sure what was going on. Standing motor cars may rock slightly, and people often describe it as similar to like a really big truck passing by the building. Sometimes people mistake it for a big truck. And then maybe some of them, it was a bit more. So this might mean that some people might even be awakened if they're asleep. Maybe you hear quite a lot of noise, the kind of walls and the windows kind of groan or crack. Not like crack as in form cracks, but you just hear them moving. And it's sometimes described as like a heavy truck actually, I'm trying to move backwards, sorry. Like a heavy truck striking the building. And then I just want to kind of point out, we're not likely to feel these kind of intensities in Cape Town. Like it's not something that you should worry about. But I just, for people that maybe are going to move to Japan or somewhere where they have these much bigger earthquakes, if you just look at some of the descriptions for these higher levels of shaking or damage, if you're maybe at something like an 8, then you would have like slight damage to specially designed structures, but considerable damage to ordinary substantial buildings and partial collapse, and great damage with poorly built structures. And you might see that chimneys fall, or factory stacks, or columns, or monuments, and heavy furniture can even be turned over. The reason that I'm kind of pointing that out is because it kind of becomes relevant in terms of what you should do if you ever are in that kind of a situation. Okay, and I just want to kind of briefly point out the number 12, which has been reported, but the description there is damage total. Lines of sight and level are distorted. Objects are thrown in the air. Okay, so if you can imagine that you can actually see the land surface moving up and down with the waves of the earthquake. So, I mean, that's only something that you would see if you were very close to the center, the epicenter of a very large earthquake, which isn't going to happen in Cape Town. Like it definitely isn't going to happen in Cape Town. But if you can just imagine how kind of terrifying that would be, that is like quite something to think about. Okay, so we're gonna talk a little bit now about the science and like how we can do stuff like understand what's actually happening in an earthquake if we feel it, and also like how we can know where the earthquakes are. Okay, so in an earthquake, you get this shaking, but there's actually different types of shaking. There's different types of waves. Okay, and the first one is called the P wave, the primary wave, and that one comes to us first, and that's basically just like a sound wave. Okay, so it moves in the direction that the wave is propagating, and often like because the wave is coming up through the earth to reach you at the surface, what that'll feel like is if like maybe the ground just kind of jumps a little bit underneath you. And it's not going to be very big unless you're very, very close to the epicenter. Often people don't even notice the P waves. If you often see like cats and dogs the P wave much more and might start barking or running around. And that's one of the reasons why some people think that animals can actually predict earthquakes. So they're not predicting the earthquake, it's just that they're more sensitive and they're kind of seeing these like early waves that maybe we don't notice. And then you have the S wave, and the S wave is moving from side to side in the direction that it's traveling. And so this is one which people kind of really know about when it reaches them, because you can actually imagine if you're standing and the earth is shifting sideways under your feet, okay? It's a very strange feeling. And probably some of the people that have described the earthquake that recently happened, they've kind of described this really strange feeling, and like it was probably the S waves there that they were kind of feeling, that they were detecting. And then after that, particularly for big earthquakes, and particularly as you get slightly further away from the epicenter, you get what are called surface waves. So that's these things up here in the center, and these are much bigger amplitude, so they're quite large, but they've got quite a long period, they've got quite a long wavelength. So what that means is they're moving from side to side a lot, but they're moving fairly slowly. So they're doing something like that, if you can see me, rather than moving really quickly, okay? And those actually often affect buildings quite a lot, particularly tall buildings. That's what causes those tall buildings to sway back and forth. Okay, so what I want to do now is I just want to show you a little video. It's not too distressing. So there's no sound on this video. It's basically some security camera footage of a hotel in Mexico, just of their pool. And what we're going to see in a minute is we're going to see the camera start to move. And that's these first waves coming in, the P and the S waves. And then after a bit, the camera's going to slow down a bit, and we're going to start seeing the surface waves actually affecting the water in the pool. And that's much more sensitive to these long period waves. Okay, so the earthquake still hasn't happened yet. You're probably maybe going to see the camera kind of move up and down to start with, and then kind of more from side to side as you get the P waves and then the S waves coming in. It's going to start any moment now. So I think you can see that it's starting to shiver a bit, right? So the earthquake's arrived. Okay, now it's moving from side to side. So these are these body waves, these quite fast, high frequency, but not very big, like quite small amplitude waves. Okay, and so it's becoming a bit more intense now. This was quite a large earthquake. So this was about a magnitude 7 earthquake, so bigger even than the one you see. So you can see that it's moving back pretty wildly. Okay, now you can see that the pool's starting to move, right? So before the pool wasn't doing anything, and now the camera's kind of stopping, but you can see the pool's moving a lot more. And this is these surface waves coming in, these really like low frequency, but big amplitude. And it's actually, like you can see in the corner, that the pool water is actually like splashed against the security camera way up, kind of like on the kind of roof of the terrace. And really, it's these kind of low frequency swaying waves, which particularly for big buildings mean you need to be very careful how you design them if you're going to get these kind of earthquakes in the vicinity. Okay, so we've seen that. Okay, so something a little bit technical, but which is maybe a bit interesting. So one thing which a lot of people have asked is like, how do we actually know where the earthquake is? How do we locate it? And we actually use these different waves to find out where it is. And the way that we use them is because the P wave moves faster than the S wave, right? So it moves about twice as fast. So if we're 30 kilometers away from the earthquake, so let's say we're station 1, so we're this station over here where we can detect the earthquake, the P wave is going to get to us in about 5 seconds. That's how long it'll take it to travel 30 kilometers. The S wave will take about 10 seconds. So the difference between those is 5 seconds, okay? And when we see that difference in travel time of 5 seconds, because we know the speed of the two waves, we can say, okay, the earthquake is about 30 kilometers away from my station. And then if we have another station, which is 15 kilometers away, then from the earthquake, that would only have a 2.5 second delay, so half as much. So basically, by looking at those delays between the P waves and the S waves, we can say how far the earthquake is from each one of our stations. And if we have 3 stations, if we know how far the earthquake is from that station, we can then draw a circle and all the points on that circle are going to be points where that earthquake could be. And if we have 3 stations, we can draw 3 circles, and all of those circles should meet at only 1 point. And that's basically where our earthquake is. Now, it's a little bit complicated than that because the 3 circles never meet in exactly 1 point because there are uncertainties. And this is something that's important in science. Our model is never perfect. And so it's always like, it's around here, but there's some kind of level of uncertainty. And that's going to be important in a bit when we talk about what actually caused these particular earthquakes. Okay, so now we're going to talk about like what happened this weekend. So there were 3 events. The first one was at about 7:10 on Saturday. That was on this plate boundary, the Southwest Indian Ridge is what it's called, and it was a magnitude 6.1. So that was the one which was like the Hiroshima nuclear bomb. So that's a fairly big earthquake, released a lot of energy, but it's a long way from us. So it's about 1.6 thousand kilometers from Port Elizabeth. And it was actually closer to Port Elizabeth than it was to us. So when we originally thought that, you know, maybe the shaking people had felt was from this earthquake, that didn't really make that much sense. It's too far away, and it would have been felt more strongly in other parts of South Africa, actually, rather than Cape Town, if it was that event. And then it became clear afterwards that there were actually these 2 earthquakes which had happened much closer. So one at 40 minutes past 8, so about an hour and a half after this initial one, and then another one the next morning, and then another one next morning, and these were much smaller. Okay. Now, these locations we know from the South African National Seismological Network, so there's like an organization called the Council of Geoscience who are always locating all of the earthquakes which are happening in South Africa. One of the questions which came through before the talk was, why didn't this earthquake cause a tsunami? Okay. Now, the main reason, well, one of the reasons why this earthquake didn't cause a tsunami, we didn't get any waves here, is because this fault here isn't actually the kind of fault which is going to give you a tsunami. So why is that? Well, that's because remember we said that you get a tsunami when one side of the fault's lifted up. So it displaces the surface of the sea. You need that vertical motion. And actually, this plate boundary here, this fault, it's actually moving horizontally. So it's like this picture that we see over here. It's just sliding past each other. And so there's no vertical motion. And so you're not going to generate a tsunami. There are some faults around here which do have a bit of vertical motion, but they're also not the kind of faults which really give you a big enough earthquake which would actually cause a large tsunami to hit Cape Town. So we're actually pretty safe from tsunamis. The plate boundary near us just isn't the kind of plate boundary that has big enough earthquakes of the right kind that are going to generate these really big waves that maybe people might have seen in Japan and in Sumatra. Okay, so let's just say, okay, another question was, did the first earthquake maybe trigger the second earthquake? Was there some relationship between them? And that's like a really hard question to answer, actually. And I actually don't really know the answer. So it's possible, is what I would say. And the reason that I would say it's possible is because when you have a really big earthquake and those surface waves that we saw before sloshing the water around in the pool, as those surface waves move through the earth, they can actually trigger little earthquakes. That's something which is known to happen. And so what this graph is actually showing you is the number of little earthquakes which are detectable as you, before and after those surface waves from big earthquakes come through. And the surface waves are coming through at this point in the middle with the dashed line. And so you can see that there are more little earthquakes afterwards rather than beforehand. So there is this effect. So basically, if you look in the lower left here, the way that we would explain that is we say, okay, we're building up the stress very, very slowly, but then as that wave passes through, it just like generates a bit of extra stress, which is then released quickly, but maybe that's enough to just tip it over into failure. So it's possible. The reason that I'm not saying this is what happened is because normally you kind of expect to see this with bigger earthquakes in the 6.1. So this study, which we're looking at here, was with magnitude 7 earthquakes, which are quite a lot bigger. And also the earthquakes that they're looking at that were being triggered were even smaller than the ones that we saw. So It could be, it's possible. It's kind of within the realms of possibility, but we can't really say for sure. And it's actually very difficult to say, this is definitely the cause of this earthquake. Like, it may have played a role, but it's very difficult to say. Okay, so we're going to look a little bit more at those little earthquakes which happen close to us, which people felt. And these diagrams, which are taken from the USGS, they have like this global earthquake information center. This is actually showing what people in South Africa felt. So this is an example of citizen science. This is an example of us being able to find out something because people actually take the time to go and fill in a form on the USGS's website as to what they actually experienced. And you can see all these little blue dots. Each one of those dots is a report from somebody that lives in Cape Town as to what they felt in this earthquake. So basically, these all represent somebody that felt the earthquake and filled in and said what happened to them. And you can see these dots are kind of blue and green. And so that means that we're seeing these intensities of 3 and 4. And so we looked at the intensities before. You know, this was like the large truck passing by, the people maybe waking up, that kind of thing. So we can see that we're not seeing these really like strong intensities, which would cause buildings to collapse. They would be in red. But we can see that all through the northern suburbs and also in Atlantis as well, people felt this event, okay? And the red stars are showing where the instruments say the event was, using that trick that we said beforehand, where we were basically looking at the distance away from each one of the instruments, and we drew the circles, and we found that there was one place where all the circles crossed. That star's basically that point, okay? So the stars are kind of north of Cape Town, between Cape Town and Malmesbury. Now, the big circles around that is basically saying, we don't really know within this kind of size, okay? So this is the kind of uncertainty of the measurement. So maybe it was actually a bit closer to where all those felt reports were, and that's why people felt it more strongly there. Maybe it's just that further to the north, there aren't so many people who live there because it's more agricultural, and so that's why there aren't so many reports there, okay? But that's something we can say about where these earthquakes actually were. Now, I just want to kind of like, before I interpret this, one of the questions that we want to ask is, well, you know, where's the fault? You know, we said before that we're building up strain on faults and then it's being released and that's what causes the earthquake. Well, where might the fault be? So to kind of understand that, there's a couple of things that we need to talk about the geology of the area. And one of them is actually that there's been another earthquake in this area, quite a big earthquake in the past. So in 1809, so quite a long time ago, 200 years ago, more or less, there was an earthquake, which is often called the Millington earthquake. And we know about it from these historical reports. And so this is like just an extract from one of those historical reports. And they talk about seeing fissures in the ground, which you could push like rods into, even up to kind of 10 feet in length. Now, that's probably a bit of an exaggeration, to be honest. I doubt there were fissures that were big, but this is the kind of thing that it kind of might have looked like. This is maybe even slightly bigger. So this is an example from Costa Rica. And you get these fissures opening up from this process called liquefaction, where basically you get the land underneath the surface becomes liquid and it causes everything above it to spread. It's the same kind of thing as caused that really crazy picture before with all the trees falling over. Now, there's a bit more to the description. So this earthquake at the time, it was actually described as like being like a volcano and there was stuff erupting out of the ground. And then this eyewitness report describes that there were all these like miniature craters, and the craters were surrounded by a crust of bluish clay, which was about 1/4 of an inch in thickness, that gets baked in the sun. And and this guy, von Buchenrode, he kind of says like, this is why people thought that there was a volcano. It was just this mud coming to the surface and spreading out. And this is something that we see in earthquakes. So the picture on the left-hand side here is a picture of Christchurch after the earthquake they had there in 2011. And you can see like all of this blue clay that's kind of covered all of the roads and the gardens. So it's the same kind of thing. This is something that we do see in earthquakes. And so we can be kind of fairly sure that this description is describing an earthquake. They're describing all the same kinds of things as we expect to see in particular settings. And there was a farmhouse called Jan Bessie's Kraal, which was destroyed in this earthquake. So it was big enough to actually kind of make a building fall down. So we have had earthquakes in and around Cape Town before. So, oh, sorry, I didn't mean to turn my video off here. Okay, so what we're going to do now, what we have here is we've got like a map of the area. We've got these 2 yellow circles, which are the earthquakes. And we're just going to talk about maybe what the faults might have been. So one possibility is that fault which failed in the 1809 earthquake. And that's often kind of drawn on as a line which sort of goes like this. So kind of underneath the northern suburbs, actually. So the places where all those people felt the earthquake. And that's often called the Millington fault zone. Now we're basing on a few kind of very old reports, so it's kind of difficult to know for certain where something is, but this is something which has been suggested, and it actually runs quite close to Coburg. So the nuclear power station Coburg is built to withstand earthquakes because of this fault and because of the 1609 descriptions. So we're safe. It's been designed taking that into account, but it is something which has happened in the past and which could potentially happen again. There's also another fault, which actually kind of interestingly runs basically between these 2 earthquakes, which is called the Calenzo fault zone. And this is a really, really ancient fault, which is like going back billions of years that it was like really very active. But it's possible that this like really, really ancient fault zone might also be being reactivated in these little events as well. So that's kind of another possibility. But because of the uncertainties, it's quite difficult to say for sure it's on this particular fault. But maybe something just to take away from this is that even somewhere like Cape Town, which is very stable, it's very far from the plate boundaries, there are actually lots of geological faults that could potentially maybe be reactivated in the right circumstances. Okay, so yeah, that's maybe the thing to take away from that. But, you know, there are candidates for where these earthquakes might be happening. I thought that I shouldn't just leave it there. I should also maybe give you like a little bit of context of like earthquakes in South Africa in general. And you can see that while you do have earthquakes in the Western Cape, actually most of them are in this area in Gauteng, which is where the mining is. Okay, so some in the Free State, some in Lesotho, a lot in Gauteng. So these kind of earthquakes are actually quite common. So a lot of these are bigger than the ones that we felt. In Gauteng, they would have been kind of probably not remarked on. They happen quite regularly. Okay, so the last thing is, what should you do in an earthquake? Okay, so the best advice, if you're inside, you actually stay inside and you drop, cover, and hold on. So you basically get underneath something like a desk or a table. And the reason for that is it's very unlikely that the house you're in is going to collapse. It's much more likely that you're just going to get something heavy that falls and hits you and injures you. So like the kitchen's a really bad place to be because you've often got stuff on high shelves and in cupboards which can potentially hurt you. So this is like the right thing to do. If you're inside, you want to cover your head, protect your head, and if you can, get under a table. Don't try and like run away if it's a big earthquake, because with those shearing waves, you're actually going to be thrown off your feet. You're not necessarily going to be able to get that far. And you don't want to just run outside of the building because this can happen, okay? So what you see here is all these bricks have fallen out of this wall here and they've collapsed around the outside of the building. And often you get things like chimneys falling down, you get bricks falling down. So that's why you don't just run outside, which is what a lot of people do. It's better to stay inside, but to try and get into a safe place like under a table and to kind of protect yourself from falling objects. And the other thing that you should probably do, or you should think about doing, is just actually making your environment safer because of those falling objects before the earthquake happens. So things like geysers, things like bookshelves, things like high, heavy objects that might fall on people. It's just something to think about, that if you secure those, you actually make yourself much, much safer in the unlikely event that we get a significant earthquake in Cape Town. But it doesn't really cost anything to do. So it's something which is worth thinking about and worth considering. And then the other thing that is important actually is that the government and the authorities and the people that do planning rules and those kind of things also think about the possibility. So like what this photo is actually showing was an exercise that took place last year in the Western Cape between the Western Cape government and the city of Cape Town, where they got together all the kind of police and the planning and the fire people, and they basically had a run through what they would do if there was another earthquake like the 1809 earthquake and what the problems might be. And it's that kind of forward thinking that you kind of actually need to try and minimize the effects. Okay, so I'm going to stop there, and I'm going to look at the chat, and I'm going to see if there are any questions, and I'm going to ask Akash if he can, if there's any questions that he's picked up that he wants to put to me.
Well, thank you very much, Dr. Sloan, for that. It was quite interesting. We've got some questions in our chat group here. One of the questions is, why are there more earthquakes in the northern hemisphere than the southern hemisphere?
So actually, that's an interesting question. And I think actually the answer is that probably there aren't, but the maps kind of make it look like there are. So the projections that we use actually make the countries in the northern hemisphere look bigger, right? And like that, the map that I showed with all the earthquakes, that was actually from a French group. And that projection, it kind of makes Europe and other parts of the northern hemisphere just kind of take up more space. And so the impression that you get from that is that there are actually more earthquakes there, or more whatever there. Actually, I mean, there's not that many in Africa, in this part of Africa, because we're far from a plate boundary, but if you go to places like Indonesia, then you actually see there are, like Papua New Guinea as well, there were loads of earthquakes there. It's one of the most active parts of the whole planet. So yeah, I wouldn't say that there's like a big difference between the northern and southern hemisphere. There is a bit of a difference in terms of where the plate boundaries are, but I think a lot of the impression that that gives you is actually from the kind of the map that people choose to show, which is actually pretty bad when you think about it.
Okay, thanks. The next question is, are tsunamis made by earthquakes we can't feel on Earth? And when was the first earthquake recorded in South Africa?
That's a really good question. So, okay, there's a couple of things. So like, there's a few things that cause tsunamis. And one of them is earthquakes. There were also other things like where you have collapses like submarine landslides and that kind of thing. So those can cause tsunamis even though there's no earthquake. There's actually kind of like very technically, there's like a type of earthquake, a special type of earthquake called the Tsunami Earthquake, which it's the same thing basically, but rather than moving really suddenly, the plates slip quite slowly. And they don't actually produce many seismic waves. You don't really feel them, but they can produce tsunamis. It's not something that you get kind of around here, and it's a bit of a technical thing, but it's a good question. Like, you can actually get these tsunamis without feeling the earthquake. And then the other part was, when was the first one? There was one which was described, written down in the 1600s. Okay, so like in the, I want to say like 1685, but that number might be wrong, but it's in the late 1600s was the first one which was written down. And like, obviously there were others before. That's just the one which is like in the catalogs as being the first.
Okay. The next question was, what is the likelihood of a massive earthquake along the San Andreas Fault causing the sort of damage we have seen in disaster movies?
So the movie, which is like called San Andreas, is like not a very realistic depiction of what would happen. But it is definitely true that we do expect to see big earthquakes on some parts of the San Andreas Fault, including the parts which are quite close to kind of major cities. And so it's something which in California they take very seriously. So the little like gifs of like people kind of like kind of screwing things into the wall and the person getting under the table, those are from something which is called the Shakeout, which is like basically an earthquake drill they do in California every year, where they basically say, okay, at this time, everybody has to pretend there's an earthquake, and like a big earthquake. And it's those kind of magnitude, maybe 7.5 earthquakes, which would cause a lot of damage that they're preparing for.
Okay. The follow-up to that was, what actually caused the Tulbagh quake, which we felt in Cape Town?
What caused which one, sorry?
Caused the Tulbagh quake, which we felt in
right, yeah, sure.
Cape Town.
So yeah, so this is the one which happened in like 1969, which is like in the mountains. So basically, you have the reason that you get earthquakes around the plate boundaries is because they're like much weaker than the places around them. So you concentrate the deformation there. But actually, everywhere within the Earth, everywhere within the Earth's surface, you're getting these stresses which are kind of gradually building up. And then eventually, those will kind of be released in earthquakes, even in places like Torbach, where it's not somewhere where, you know, we can see there's definitely a large concentration. So it's like not so much that you necessarily need to have like a trigger or a cause necessarily. It's just something which can happen just because they've got these gradual stresses building up and it's happening all around us. So one way that we can understand this is like if you actually fill a reservoir, like if you make a big reservoir and you fill it with water, so like they did with the Kariba Dam in Zimbabwe, you almost always get lots of earthquakes afterwards. And the reason for that is because almost everywhere there are these stresses which are held in the earth, and if you change the stress, which you can do by filling up a reservoir above it, then it will actually trigger them. Okay, it can lead them to cause. So you can get them almost everywhere. It's this gradual process. We can't say like, you know, it happened in Torbach for this particular reason.
Thanks. And what is the average amount of earthquakes daily worldwide?
Well, okay, so the thing is, you get earthquakes of all sizes, right? Like, I mean, most earthquakes you can't even feel, right? So, I mean, we had a deployment in Namibia where we did like with the research group, we put out stations around a particular fault. In this place, which is like, you know, it seems completely stable, we recorded hundreds of earthquakes in a few days, just in that one tiny place. But they're very small, you don't feel them. So, I mean, there are actually millions of earthquakes, like countless earthquakes, which are happening every single day. It's just most of them are so small that people don't feel them. And if you remember the figure that we had before, that gives you kind of an idea of like 1 week's worth of like big earthquakes. And there you saw that there was maybe, I would say, like in the order of like 100 or 200 kind of earthquakes big enough that you can feel them in a week. Okay, so that gives you kind of an idea.
Okay. One of the questions is, if an earthquake is too big, will it separate an island?
Yeah, so like, I mean, it's kind of interesting, right? So like a single earthquake isn't going to cause like an island or something like that to separate out. But when you have these rifts, so you have something like the East African Rift, as you have earthquake after earthquake over thousands, over millions of years, gradually you do actually start to split apart the continent, the land that it's on, and you actually create an ocean in between. So not one earthquake, you can't have one earthquake that's that big, but like over time you absolutely can with these repeated earthquakes.
And what's the biggest earthquake?
What's the biggest earthquake? The biggest earthquake's just over a magnitude 9. Okay, so remember that like each time you go up 1 order of magnitude, it's 32 times more energy. And that magnitude 9 earthquake means that you're talking about something like 1,000 kilometers of fault which ruptures in a single event. Okay, so you can kind of imagine how big that is. And that's probably the biggest you can get just because you're limited by the size of faults. Like the subduction zones are where you get the biggest faults that can rupture continuously, but like there's a limit to how big a fault is ever going to get, and that gives you your kind of maximum limit of how big an earthquake could be.
Interesting. Do underwater earthquakes affect the sea life?
I'm unaware of the research on that. I'd be very interested to know. I don't know. I think probably not. I think probably the sea life's okay. I think, but yeah, I certainly am. I'm pretty sure that it's not like you kind of get like dead whales washing up after kind of these large earthquakes. That isn't something that I'm aware of. So I think they're probably okay, but I'd be open to correction.
Do you get different stages of an earthquake?
Yeah, you actually do. So, I mean, it depends on what you mean by that question. So like in terms of the earthquake cycle, you get kind of that gradual build up and then the sudden release. And then afterwards, you get this period where you get like lots of aftershocks potentially for big earthquakes. And you can get the fault kind of continuing to slip for a while. It's called like the post-seismic phase. So in that sense, there is like you know, like a series of stages that it's going through. And then the other thing is, like, in terms of the different stages of the earthquake, what people experience, it's these different waves coming in. So the P waves, and then the S waves, and then the surface waves. Your experience of those is quite different. And so I think that's another thing that people often kind of describe a double shock, and it's the P waves and then the S waves coming in afterwards.
Okay. See, the next question is, how deep can an earthquake be?
So that's also a good question. I like that question. So like basically you get earthquakes close to the surface because the rock has to be cold enough to break rather than flow. As you go further down, the bit where it's convecting, it's the hot materials rising up and it's sinking down. That's basically, you can't get earthquakes there. But there are these places in this kind of convection system where you get the oceanic plates being pushed down into the mantle, okay? So you've got this cold thing which is going down at maybe a few centimeters per year. And actually it takes it a long time to heat up. So you actually get earthquakes all the way down to about 600 kilometers depth in these cold material being pushed down into the hot interior. And then once it gets about 600 kilometers, it'll have heated up enough that you won't get any more. But good question. I like that one.
Will earthquakes become more frequent as the Earth gets older?
So probably actually the opposite, right? Because you're kind of driving this system by this heat rising and then it cooling and then sinking. And gradually over time, the Earth's actually going to cool down, like it's cooling down all the time. We're losing heat into space. So over very, very, very long time periods, eventually there'll be less earthquakes, it will be less active. And like in some of the smaller planets in the solar system, they probably were active, they probably did have this kind of like tectonics at once in the past, but now they've actually cooled down enough that you don't get the same forces, and so you no longer get the same kind of plates moving relative to each other. So in billions of years, but yes, it will probably get less.
Okay. And what type of energy do earthquakes use?
What type of energy? Well, it's this elastic energy. So you're gradually storing up elastic energy, and then it's that elastic energy being released, which is basically causing the earthquake, causing the damage. And actually, as it travels, it's also traveling as elastic energy as well, because what's basically happening is the rock's being bent, and then it's snapping back, and that's the wave that propagates through the Earth. So it's elastic energy, like an elastic band.
This is an interesting one. What is the biggest earthquake you have actively studied, and where?
So I've studied quite a lot of earthquakes which are kind of around the kind of magnitude 7 and a bit mark. So like 7.2, 7.3. And in terms of where, so one of them was in India, like kind of similar to here. It's like in the middle of the plate. It's one that happened a long time ago. So a lot of the earthquakes I study maybe happened like thousands of years ago. And we're looking at the record in the landscape so we can get an idea of how big an earthquake can happen in this place. Actually, we're studying a fault in Namibia at the moment, which we think might have actually failed in a magnitude 7 kind of size earthquake as well. So that's like something which is like maybe a bit more surprising. And then also like the same kind of size in Iran and Mongolia as well.
Okay, I'm just going to take a few more questions before we have to end the session. But according to research, are the number of earthquakes globally increasing? And if so, why?
So no, they're not globally increasing. So like I would say that probably we're getting more and more instruments, so we're better able to detect smaller and smaller earthquakes. So we're maybe when we plot the map, you see more and more earthquakes as you kind of go through time, but it's more about what we can observe rather than what's happening naturally. So basically it's pretty constant. If you take the kind of billion-year timescale, which geologists quite like to do, you might say you expect it to go down. But in human timescales, it's going to be pretty consistent.
Okay. Was the second quake at 12 minutes
yeah,
past
I think
one?
that was actually. I think that was actually a typo. I'm sorry about that. I think it was actually
Okay.
should be. It should be like 10 a.m. Like yeah, I kind of noticed that as I was like giving the talk. I've got it written down here. So the second quake was at 12 minutes past 9, not 12 minutes past 1. So
Okay.
yeah, thanks for that keen error spotting, fact checking there.
Have you ever personally experienced an earthquake? And if you have, what was the magnitude?
So I have, and it was in Cambridge, and it was about the same as the earthquake we experienced here. And I haven't experienced anything bigger than that, which I'm quite grateful for. I think like one thing which I haven't done is I haven't done research in the immediate aftermath of a large earthquake. That's something which some people do, and maybe I'll do it at some point. And if you do that, then you're likely to feel aftershocks. But yeah, no, just a minnow like the people in Cape Town have experienced.
Okay. There's one here that says, that asks, can earthquakes be produced artificially by humans, such as in a testing environment, in order to study earthquakes more?
So surprisingly, maybe yes. And actually the experiments have been done. They were done in the US. So basically, if you pump in water, pump in liquid into the subsurface, into the ground, that can change the stress state to kind of actually trigger an earthquake. And there was a place called the Rocky Mountain Arsenal in Colorado, where they were disposing of the material that the United States made during their chemical weapons program back in the 60s or 70s. And as they were disposing all these nasty chemicals by pumping them underground, they suddenly started getting earthquakes in this place. There hadn't been earthquakes before. So they experimented with like pumping more, pumping less, and see how the earthquakes changed. And then there was like actually a magnitude 5 point something, which damaged some buildings in Denver. And they were like, okay, we have to stop now. This was probably a bad idea. So you can actually generate earthquakes, mainly by pumping fluids down into the earth. And yeah, there have been some experiments on that, possibly unwise ones, but interesting.
What earthquake did the most damage, and in which country was it?
Interesting. Probably in China. So there's been a few kind of big earthquakes in China. One of them was the Tangshan earthquake, which was back in around the 70s. And that's widely thought to maybe have killed the most people. And you're talking, I mean, I think the official estimates were hundreds of thousands of casualties, of fatalities, and unofficially, it could have been even worse. So yeah, China probably has been unfortunate enough to have the kind of the most devastating earthquakes.
Okay, I'm just going to take the last two questions. Are earthquakes important to any positive ongoing Earth systems? And that is, if they stopped, would anything detrimental to life occur?
That's another really interesting and good question. The Earth is a very complex system. And so the repeated movement of earthquakes, right, this plate tectonic system, it actually does a whole variety of things. Like it actually puts water down into the mantle, which affects how the mantle moves. It exposes fresh rock at the surface all the time, which is actually one way of consuming carbon dioxide. The weathering processes in that can actually like act as a sink of carbon dioxide. So one of the kind of beautiful things about geology is that the Earth is such a complex system that everything interacts with everything else. And so like actually the fact that plate tectonics happens affects things like evolution. It affects things like climate change. And so if you were to just stop it, then it probably would be a problem, actually. There would be negative impacts of that, sadly.
Okay. And one question we received prior to the webinar are there any scientific proof yet that earthquakes are influenced by our level of corruption and sins?
Yeah, so that is an interesting question. So that's something which is a very common belief, right? So like in a lot of places, a lot of people will say that an earthquake happening is a punishment and that it's maybe God's will. The problem with taking that view is it basically means that the kind of authorities and the people don't need to prepare for it, okay? And given that we know that like, you know, you have a fault, which is an active fault, particularly on a plate boundary, there is going to be an earthquake in a reasonably regular period. It is going to happen regardless of how people behave. And so it's dangerous to maybe put it think of it in those terms, to think of it as a punishment, because then maybe you feel like you don't need to prepare, the politicians feel like they don't need to prepare. In terms of corruption, then there are big effects in terms of earthquakes and corruption. So there have been studies looking at like corruption, particularly in the building industry, and the effect on fatalities in earthquakes. So in countries which have a more corrupt building industry, you have many, many more fatalities in earthquakes, even when there are smaller earthquakes or less common earthquakes. So like how you build your buildings and whether or not they're built responsibly has like a big effect on the effects of the earthquake. So not how many earthquakes there are, but whether or not those earthquakes are going to be a problem for people. Because there's like a saying in the kind of field is that earthquakes don't kill people, buildings do, right? Like if you're in a well-built building, you're completely safe. Like in Japan, where they have these huge earthquakes, people in skyscrapers can just sit and wait for it to pass, and they'll be fine. So yeah, there's like maybe a bit of a thing there. I see there was one other thing. Somebody asked, do earthquakes affect animals? Like we're talking about the sea animals. Like one of the things, there's a lot of descriptions of like animals maybe kind of predicting earthquakes. And it does seem to be true that animals, they're maybe more sensitive. Some animals are more sensitive to the small vibrations. Like I guess in kind of the same way as like dogs are very sensitive to kind of quiet sounds that we can't hear. One of the things which I did to kind of prepare for this talk was I spent a bit of time today looking at YouTube videos of earthquakes, of people responding to earthquakes. And very often in those YouTube videos, the first sign that something's happened is the cat kind of rushes across the room in like an absolute panic, or the dog starts barking. And that's the P wave arriving, and the small waves like affecting the animals. And then the humans maybe like go like, oh, what was that? And then the S waves come, and then everybody knows what's going on. So yeah, it's kind of interesting to see how they interact with them.
Okay, I'm just gonna ask you one last one. Is there
Okay,
a relation between volcano eruptions and earthquakes?
So yes, there absolutely can be. So like often before a volcano eruption, the magma has to move from deeper down in the earth up towards the surface. And as it does, it kind of breaks, it splits the rock, it's changing the stress state. And that process is usually associated with lots of little earthquakes. And sometimes if you have a big earthquake in the same area, and both earthquakes and volcanoes often happen in plate boundary areas, so they kind of are often kind of close together. Again, like with a big earthquake, all the shaking can sometimes trigger an eruption. So there is a link between them. Like the movement of the magma is almost always going to be associated with little earthquakes, and sometimes you get these big earthquakes which are also associated with eruptions at the same time. So that's also a good question.
Wonderful. Well, this brings an end to tonight's talk. Thank you, Dr. Sloan, for that very interesting talk. And thank you to all of you for joining us this evening. Be sure to look out for more exciting talks and activities we will be having over the upcoming weeks by following us on Facebook and checking us out on our website, www.ctsc.org.za. Until next time, take care and have a fantastic evening. Thank you.
Thanks, everyone.